and y as long as it's not zero, the DC component will increase with the time t until saturation. As we can see from the equation 1, there is a pure integration link in the voltage model. The pole of pure integration link is located in the center of the S plane, which determines that the pure integration is very sensitive to DC offset component. Drift in the peak signal and changing motor resistance, particularly if the motor is working at low speed. Theoretically, when the input signal frequency is zero, the gain of integrity is infinity, which means that even a small DC offset input will lead to large DC output, producing a large DC component in the output signal until saturation. So in this scenario, the actual rotor position is not same in phase with the estimated rotor position, as we can represent in the equation 3. So therefore, in case of DC offset, conventional voltage flux observer cannot precisely estimate rotor speed and position. This is the conventional voltage flux observer. And conventional voltage flux observer uses stator voltage and current and transform from three-phase to two-phase observer stationary phase alpha beta plane. This is the main block diagram of conventional voltage flux observer. And for theta estimation, some researchers they propose a tangent, and some they can use PLL to estimate the theta of the PSA rotor. So now we talk about our proposed design method to achieve a more precise rotor position and improve flux observer with the ADRC DC offset compensation is presented in this section. As we can see, we use a stator current to estimate the flux linkage, and this, as we can see from the equation 4, there is a no integration link is involved to estimate the stator flux, as well as there is no voltage, a stator voltage involved into estimate the flux linkage observer. So in this, as we estimate the flux from the stator current using equation 4, so there is no DC offset. And the equation 4, the I alpha ID IQ is represent the stator current and DQ frame. LD and LQ is the inductance of the motor, and we can transform the flux from DQ frame to alpha beta by using a transformation from alpha beta to DQ to alpha beta transformation. So the main point, the main research, our target is to remove the DC offset from the system. So as we can see, the if we estimate the flux from the traditional flux observer, so due to the DC offset in the voltage signal, so this part is always exists a DC offset. But if we estimate flux from the stator current and using the rotor position angle, this part no DC offset. So this estimate the DC offset error compensation composed of two parts. The first part is we minus the actual flux minus estimated flux. Like the flux we mirror from the integrated flux linkage minus use the stator current. So then the error is input. The error is input to the ADRC, and the ADRC estimates the exact ADRC value which is exists in the system, and we minus from the weak EMF signal. The design ADRC controller output is updated in real time to obtain the real DC offset value constant. So now in this section, we will verify our proposed method by simulation environment. In this portion, MATLAB simulation study are investigated to verify the performance of presented work. The effect of model simplification on the position estimation error under DC offset and speed condition is examined. The FOC control scheme is implied as the main control scheme. Following the performance of steady state and dynamic state position estimation is studied. Furthermore, the machine flux linkage performance is also investigated. And table 1 display the motor parameter which is used in the simulation in one studies. First, we talk about the traditional flux observer and the figure 6. As we can see, when we estimate the speed from the traditional flux observer in the ideal situation, like there is a no DC offset error in the system, the traditional flux observer can accurately estimate the speed, flux, as well as the position of the rotor. Whenever we inject the DC offset signal, the voltage of 0.11 at 1.5 second, as we can see the fluctuation, the estimated speed, and we can also observe the drift and the flux linkage, and we can also observe the large oscillation and instability and the angle estimation using the traditional flux observer. So now we talk about our proposed method and the low speed domain. In figure 7, simulation waveform are the estimated rotor position error and the DC offset compensation of the motor synthesis control. When a 0.7 volt DC drift error is added to the at 0 second to the back EMF signal, the back EMF and its angle estimation maintain the series pulsation. With no delay, the proposed strategy initiate DC offset error correction in real time. The amplitude of DC drift error is increased from 0.7 to 1, 1 volt to 1.5, and 1.5 to 2 volt at 2.1, 3.9, and 5.6 second respectively. As we can see from the picture, we inject 0.7 volt in the 0 second, and then we increase the amplitude to 1 and 1.5, 1.5 to 2, etc. So as we can see, when we inject the DC offset to the system, we can see the oscillation in the estimated rotor position angle. But due to the our proposed method, the disturbance is removed, and we can estimate the accurate rotor position of the IPv6. As we can see, the flux linkage, state of flux linkage, we use our proposed method, and whenever we inject the DC offset at 0 second, we can see some small overlap. There's a small disturbance whenever we inject the DC offset, but due to the proposed ADRC approach, remove the DC offset and the flux linkage constant convert to its true value. The flux linkage oscillation is effectively reduced through the DC drift compensator, and EDRC controller and constant value is maintained. Figure 9 show the simulation waveform of dynamic speed estimation using a EDRC DC offset compensator. As we can see, if we inject the DC offset, the different amplitude, we can see some disturbance initially, but due to the proposed EDRC approach, smoothly remove the DC offset and the flux linkage constant convert to its true value. So henceforth, the result demonstrates that the estimated flux are extremely closer to the actual value. When the DC drift error value is increased, both the speed and flux estimation remain stable in steady state. We can see some in dynamics. We can see some fluctuation, variation between actual speed and estimated speed, but in steady state, there is a zero error. In the steady state, the transient estimation of the speed has minimal ripples and high precision. So we show different condition whenever we inject 0.7 volt DC offset to the system, and we inject 1 volt and 1.5 and 2 volt. We see some fluctuation between estimation speed and actual speed. But due to our proposed method, this disturbance is removed within less than 1 second. So, conclusion of our proposed work. Unlikely traditional low-pass filter, self-adaptive band-pass filter, and high-pass filter, this is a proposed and improved flux linkage estimation approach with active disturbance rejection controller, DC offset compensator, resolve the DC drift issue associated with the observed pure integrator. Successfully remove the endplanes of DC drift in the baking map and achieve zero steady-state error flux observation. Control speed and steady-state accuracy are both improved with the position sensorless control system equipped with the ATRC controller, providing the effectiveness of the proposed controller. Significantly improved system performance at low and medium high speed area. Adaptive composite algorithm can be accurately estimate the rotor position in the wide speed range. With the advantage of high accuracy, high dynamic performance, and high flexibility in trajectory, the proposed flux estimator can greatly expand the scope of application of sensorless control in surface permanent magnet synchronous motor and interior permanent synchronous motor, which lead to industrial scenario significance. That's all this much. Thank you very much.
Uh, Thank you and very nice presentation, Mr. Sadiq.
Thank
You
thank
have
you.
presented very detailed means presentation, so I'm sure means every results will be very fine. I have just one question. Since you are using the controller, so is there any harmonics involved into that one?
In this research, we just focus on the DC offset. Whenever the DC offset in the stator voltage, so how they affect the rotor position estimation and how to solve the problem. We did in research on the harmonic. This is our future work.
Okay, thank you very much, Mr. Sadiq.
Thank you.
So now we
Thank
will
you.
go for the next presentation. So next presentation, I'm inviting Mr. Wakara Ali from Mehran University. And the title of the presentation is Performance Assessment of Multi-Phase Switch Reluctance Machine for Wind Energy Applications. So Mr. Wakara Ali, you can share your screen. Mr. Wakara Ali, please share your screen. Can you hear us? We cannot hear you. Maybe your mic is off. We can see your screen, but your voice is not coming. Can you check it? No. Mr. Vakar, please adjust maybe your mic or hardware or some problem. We cannot hear you.
Ask him to change the mic.
Yeah, I think you need to adjust properly or change the mic because sometimes some noise came, but still it's not working. No, we cannot hear. I think
To his mobile phone.
no, we cannot hear you. Maybe your mic has some problem. Maybe you can join us with your mobile phone for the audio.
अस्सलाम वालेकुम। हेलो अस्सलाम वालेकुम। हेलो अस्सलाम वालेकुम।
Mr. Vakar, are you there? Because we cannot hear anything from your side.
Sir, I am here. Are you hearing me?
Yeah, can you speak a little loud?
Yes, sir, sure. Can I share my screen now? Sir, can I share my screen now?
Yeah, you can share your screen.
Can I present, sir?
Yes, you can make slide view and you can proceed.
Okay, sir, sure.
Can you go to the
My,
presentation mode?
yes, sir.
Can you move your slide to the presentation mode? Yeah, can you move to the presentation mode, or you can, if you have problem, then you can start, please.
Sir, my presentation is visible to you.
Yes, we can see the your presentation, but if you move to the slide mode, then we can have the full screen. Or you can proceed.
Okay, sir. So the title of my presentation is Performance Assessment of Multi-Phase Switch Link Touch Machine for Wind Energy Application. These are my contents. My abstract is the adoption of renewable energy sources, particularly wind energy, has been remarkable growth in recent years. Wind energy generation requires efficient and reliable generators that can convert wind energy into usable electrical energy. Swift Lantern generators have been gaining popularity in wind energy applications due to their high efficiency, reliability, and low maintenance requirements. These generators are used especially in wind power plants due to ability to operate in variable speed range. In this paper, a model of Swift Lantern generator in MATLAB is presented. The obtained results showed good agreement under different operating conditions. The operating results are current voltage, torque, speed, flux, and angle of generator. These are shown in graphs. Sir, my audio is clear. Can I proceed?
Yes, you can proceed. We can hear you.
Okay. So this is introduction. Energy is considered a backbone of any economy and plays an important role in socio-economic development of country. Electrical energy is one of the most widely used kind of energy in the world. It can be easily converted into any other energy type and transmitted over long distances safely and effectively. The electrical machine converts energy between electrical and mechanical power in both directions. Electrical machine can be utilized for varied ranges of speed. It can be employed as generator in power plants, wind turbines, etc., or as a motor, particularly in traction electrical wheels, etc. The attraction of such reluctance machine is due to its simplicity, performance, and high starting torque. The simplicity of machine reveals from its construction as bindings are found on stator only. The phase arrangement is distinctive if compared with induction and DC motors. Therefore, such reluctance motors available in different phase arrangements such as 2-phase, 4-phase, 6-phase, etc. The addition of phases may be advantages and disadvantages, such as less or more torque ripple and additional losses due to number of additional electronic devices used in the converter of the machine and copper used in the phase windings. For wind energy application, the consequences of greenhouse emission gases are recognized by international communities, and climate change is current topic. Renewable energy is one of the best solutions for reducing emissions of greenhouse gases. One of the major solutions for reducing greenhouse gas emissions and carbon dioxide from our environment is wind generation, which is one of the renewable energy power source. Two types of wind have been used in wind energy generation system. fixed speed wind and variable speed wind turbines. Recently, the variable speed wind turbine is preferred due to their high efficiency in variable speed wind convergent energy system, doubly fed induction generator, permanent magnet synchronous generator, and surge reluctance generator are used as generator. Among these generators, surge reluctance generator have many advantages such as its simple and robust structure, low cost, and high efficiency. Also, it has no windings and magnet in the rotor. It is only wound on the stator poles. For this reason, heat losses mainly occur in the stator. This feature allows for easy cooling and operation at high temperature and speed. Its another advantage is that there is no connection between its phases. In this way, any error occurring in any phase does not affect the others. Thus, its fault tolerance is high. In addition, the unipolar current requirements of phase windings in switch reluctance generator make a simple and reliable power converter. Switch reluctance machine performance as generator. Switch reluctance machines have shown promising performance as generator in various applications. They can operate a wide range of speeds, allowing for efficient power generation in different operating conditions. Also possess inherent fault tolerance as they continue to operate even in the presence of certain faults or irregularities in the system. Circular machines typically require advanced control strategies to optimize their performance and overcome challenges such as torque, ripple, and acoustic noise. Ongoing research focuses on improving the efficiency and power quality of such reluctant machines as generators, as well as exploring their integrating with renewable energy sources such as wind and solar. Overall, such reluctant machines demonstrate considerable potential as generator and continue to be an economic social development. These are some pictures, cross-sectional view of switch reluctance machine, and this is four-phase switch reluctance machine. This is literature review. These authors have these are some research papers of authors. These is previous work. Design and optimization of switch reluctance machine for performance and reliability enhancement. A comprehensive review of literature on the state of art, emerging trends, and design optimizing techniques for switch reluctance machine, covering design theory, electromagnetic and thermal modeling approaches. Novel topologies, optimization, classification, and methods for improving optimization, effectiveness, and outcomes. Number second is performing analysis of rewound multiphase synchronous reluctance machine. The performance of switch reluctance motors when a three-phase stator is rewound to a higher number of phases is examined. The newly developed rewinding method provides a similar harmonic air gap flux distribution, a greater winding factor, and a large value for the fundamental magnetic force component. Control of switch reluctance generator and wind power system application for variable speed. Propose a simulation of switch reluctance generator driver in MATLAB or simulating and real-time implementation. Control of switch reluctance generator is carried out. The output voltage of switch reluctance generator is controlled by a proportional integral voltage controller. As a result, the graphs of change in switch reluctance generator phases, currents, and switch reluctance generator output voltage are obtained according to different parameters. Modeling, design, optimization, application of switch reluctance generator machine. Switch reluctance machine. Sorry. Propose the mathematical modeling of electromagnetic and thermal field in switch reluctance machine. Improvement of performances in terms of torque, ripple, acoustic noise, efficiency, torque, density, and multi-objective design optimization incorporating all of the mentioned factors are covered in the study. Nonlinear modeling and simulation of four-phase switch reluctance machine for wind energy. Propose a switch-reluctance generator modeling technique for wind energy application that is based on non-linear inductance model and electromagnetic field. Results from modeling and simulations are presented for switch-reluctance generator. Performance analysis of various configurations of switch-reluctance machine for wind energy. Presented switch-reluctance machine with various winding architects is suitable for the use in the variety of application. A performance analysis of switch reluctance machine using SRDA switch reluctance design and simulation software program is described. This is summary of literature review. Many research have carried out for switch reluctance machine, including design, modeling, simulation, performance, but is also necessary to discuss the multi-phase switch reluctance machine. because it is a many application including wind turbine. Switch reluctance machine is a variety of application including wind turbine, windmill. In this research, multi-phase switch reluctance machine is described, modeled, and simulation also given, and its application wind energy also discussed. This is problem statement. The requirement of generator for wind application is such that it should continuously work even in case of fault. Reason being that wind turbines are located away from city centers in the remote areas having less facilities of repair and maintenance. In such case, multi-phase machines are highly prioritized. The purpose is that machine should not stop work in case of fault. It should operate until its fault is repaired. These are aims and objectives: to develop a simulation model in MATLAB of four-phase switch reluctance machine, to investigate the operation or performance of switch reluctance generator, switch reluctance machine, and obtain different results such as current, voltage, speed, torque, flux, and angle of generator. This is research methodology, literature review, simulation model using MATLAB, comparative analysis of performance of switch reluctance under different operating conditions, compare results with existing research. This is simulation model and results. Using the MATLAB or simulating a mathematical model for switch reluctance machine was created, in which we have connected switch reluctance machine directly with the wind turbine and is operating as generator. For simulation purpose, rated voltage taken is 200 volt, turn on angle is 13 and turn off angle is taken as 23. By simulating the model, output current has been investigated. Output voltage and current of generator is shown in figure 5. We can see that during startup, generator output current exceeds but is controlled by excitation circuit. Since then, no disturbance is detected in generator current value, which validates the performance of switch reluctance machine. Further, output torque and generator speed are also shown in figure. The generator flux and angle of generator is shown in figure 7. This is excitation circuit of switch reluctance generator. Excitation circuit act as feedback circuit that control the magnetic flux of generator, which in turn alters the current. In the result, the current alters the voltage. It has sensor that provides position of rotor and timing of circuit and adjust the timing of the output values to generator. This is a complete MATLAB model of switch reluctance machine. Is act as switch reluctance generator for wind energy. A wind turbine has three inputs: generator speed, pitch angle, and wind speed. Output of wind turbine is torque in per unit. Generator use the machine used as generator. The switch reluctance generator takes input from excitation circuit and provides output like voltage, current, and speed. These are result. This is generator output voltage, and this is generator output current. These results are output torque and speed, and these are flux and angle of generator. Further conclusion: the performance and efficiency of wind turbine can be significantly improved. According to research on switch reluctance generator for the wind energy application, switch reluctance generator unique development and functional characteristics have number of advantages including cost, effectiveness, robustness, and adaptability for varying wind conditions. Although switch reluctance generator showed great promise for wind energy, there are still challenges that need to be addressed. Further research is required to optimize switch reluctance generator design for a specific wind speed regimes and to improve their scalability and cost effectiveness. Additionally, studies on the long-term reliability, maintenance and requirements and environmental impact of such reluctance generator and wind energy system are critical for their successful development on a larger scale. In conclusion, the research on such reluctance generator for wind energy has provided valuable insights into their potential benefits and challenges. Continued efforts are needed to ensure that the machine perform optimally and provide reliable and sustainable performance.
Thank you, Mr. Vakar, for the nice presentation. So I have one question. So did you verify your simulation result with the some practical application or with existing work of other researchers? Can you hear me?
Yes, sir. Can you
Did
repeat your
you
question?
compare your result with the existing work of other researchers?
Sir, work I have not mentioned here.
Did you compare your result with other researchers working in the similar field?
Sir, can you repeat?
Okay, the work you did you have simulation result? Did you verify with some practical?
Sir, I have compared, but I have not mentioned here.
Okay, okay.
I think this is the end of this session. So thank you all the presenter, Ms. Zaina Binti, Mr. Mohsen, Mr. Sadiq, and Mr. Wakar. Very nice presentations from you all, audience, from all. And as a session chair and the audience, we have learned a lot. So all the best, all the presenters.
Okay, thank you for you can join the other sessions online in parallel and have a good day.
लेकिन माइक मेरे पास है इसमें